and like I say, if things locked up, just don't go away mad. Don't go away at all. Just wait. Okay. Well, thank you, Yang Quan, for inviting me. It's the new semester for you guys, I guess, right? This is your first meeting of your class, and so I think it's good to. And so I appreciate this opportunity to speak to your lab group and to you guys out there. I wished I could come visit in person, and maybe next year I'll be able to do that. Okay, so what I'm going to talk about today is some work I've been doing applying fractional calculus to magnetic resonance imaging, particularly relaxation and diffusion measurements in MRI. So I have a summary here. This is a cartoon I took from an English magazine, Punch. Gentlemen, this is just to give you an idea. Actually, there are lots of wires and things. So the guy is holding up a light bulb, which is illuminated and it doesn't say anything about the what's going on in the background here. So the idea I'm going to talk about today is using fractional calculus to garner or gain information from the data and the procedures that you use in magnetic resonance imaging, particularly in the development of contrast in magnetic resonance imaging. So the basic idea is to see if fractional calculus models of relaxation and diffusion can capture some of the complexity that we know exists structurally and functionally in the brain and in the body. In particular, we think fractional calculus works because it gives us an adjustable order in our modeling. I think one of my students, Carson Ingo, had this slide, and I think I stole it from him. Where integer calculus, I think of as a set of wrenches that are fixed, whereas fractional calculus, you have an adjustable wrench that you can apply, you can adjust the order to maybe fit the problem better. And if the models work at capturing complexity of structure and function, then it would be prudent to then apply them to see if they are sensitive to changes in those parameters, particularly those kinds of changes that arise with disease. There are some examples I'll show from some of my work and work of my colleagues, focusing on things like Alzheimer's, Huntington's, and brain tumors. No COVID, I haven't gotten into that. Okay, I want to first provide some context and some connections. That is context for fractional calculus and magnetic resonance, and the connections between those two circles and what goes on with relaxation and diffusion. In an overlapping Venn diagram sense, we can look at magnetic resonance. It encompasses at least two main disciplines, that of nuclear magnetic resonance, which some of you who have had organic chemistry will be familiar with because NMR spectroscopy is used for determining structures unambiguously, and MRI, which has medical applications.
We're having a freeze. Don't worry, it will coming back. Yeah, I'm glad to see the random processes.
Is the waiting time distribution?
That's probably because of the long waiting time and jump length.
Alpha stable distribution for network communication delay, Dr. Chen.
So that's considered as a normal. Abnormal is normal. So I think he lost the contact. He may join us again. So don't worry, let's wait. Oh, we have a Kai here. Oh, don't worry. Let's restart.
Okay.
The recording is not discontinuous, it's continuous.
Okay, so let me go back to where I was. So,
okay.
So can you guys see the slides still?
Not yet, you haven't shared the screen.
I have to go back and share the screen again. That's the problem. Yeah, okay. Yeah, so when I log out and come back, then I've got to go share again. Sharing. Okay, now you see the slides?
Yes, that's excellent. Yeah, Venn diagram, yeah.
Okay, back to the Venn diagram. Okay,
Yes.
let's try it. Okay, good. I mainly talk about applications involving continuous time random motion, random walk, and fractional motion, the so-called CTRW and fractional motion models. I'm assuming I'm talking to people that are in your lab and they know as much about or more fractional calculus as I do. So I'm not going to waste any time going through the usual suspects. We're going to go right to it. I am going to try to point out that the random processes overlap with magnetic resonance in the particular fields of diffusion and relaxation, because it's the motion of water molecules that are detected in MRI, and its restrictions on that motion, their rotation, their translation, that affects the relaxation times and the diffusion measurements that are used to generate contrast in an MRI image. So I'm assuming everybody knows everything they need to know about fractional calculus, and I'm ignoring all the details that one needs to go through in order to generate magnetic resonance images. I'm only going to talk about the contrast, and the contrast in those images is going to be flavored by fractional calculus models of diffusion and relaxation, and that's where the overlap will be. So much for context. The connections, well, fractional calculus, as you know, is applied everywhere. I mean, you guys do it in all different aspects of control and electromechanical systems and robotics and everything. Initially, it was very successful in electrochemistry, in dielectric modeling, and in viscoelasticity. And since it works with the mathematics that underlies these processes, it can be extended to almost anything. Within magnetic resonance, it too has subflavors or specialties, electron spin resonance, nuclear magnetic resonance, which I mentioned, and magnetic resonance imaging. We're going to look at MRI, and in particular, we're going to look at relaxation and diffusion as processes that occur in tissues that are amenable to detection using MR specific pulse sequences. In the classical sense, you measure a relaxation that's an exponential process, and you have relaxation times. They're time constants. They're not RC or L over R, they're T1 and T2. In the case of MRI, with relaxation involving anomalous behavior, we know that in general, the exponentials morph into the Mittag-Leffler functions, and what we obtain are still relaxation times, but we also have the adjustable parameter of our crescent wrench. We have the fractional order of the time operator, for example. Call it alpha. Diffusion, of course, is another area that is used in MRI, particularly the diffusion is assumed in most situations to be Gaussian. The diffusion constant can be directly measured, and by measuring gradients in different direction, you can determine the tensor relationships, so-called diffusion tensor imaging, and with that, you can map fiber tracks. So all sorts of work is done with the existing mathematical models, and they're very fruitful and useful. But in some cases, they don't capture everything, particularly when the processes are non-Gaussian. Then one looks for other tools. Fractional calculus models are convenient tools to apply in this situation because there's a lot of fractional diffusion processes that are fairly well worked out. In this case, we look at situations where we have perhaps a fractional space and a fractional time derivative. So we may get things like Mittag-Leffler functions, our old friend, as Professor Minardi calls them, the queen function of fractional calculus. But in addition to this diffusion tensor, we're going to get maybe alphas and betas that are related to the order of the fractional time and fractional space derivatives. So we're going to look right at the intersection of these areas of magnetic resonance, fractional calculus, and random processes. We're going to focus in on relaxation and diffusion. First, I'll talk about relaxation, and then I'll go on to talking about diffusion. I threw some, I'm shamelessly dropping names here. You guys know all the names or a lot of the names in fractional calculus, but I just point out that the contributors to the random processes that are the underlying basis of diffusion and relaxation are almost as distinguished, or perhaps even more distinguished, than the mathematicians that provided foundation for fractional calculus. And magnetic resonance has its own set of significant contributors, most of whom have collected Nobel Prizes. So let's talk about relaxation. The governing equation, the plant model, if you guys want to think of a control mechanism, involves the time rate of change of the magnetization that's induced in the water protons. And this time rate of change of magnetization is related through a precessional gyroscopic motion that allows you to apply magnetic fields, so-called B of t. It's really B of x, y, z, and t, but just for simplicity, I've made the x, y, and z a vector, and the t the time dependence, because that's the thing we manipulate most. And then the components of this magnetization. So this is really a set of 3 scalar equations, and they're cross-coupled and they're bilinear, and in general nonlinear, but it involves a time rate of change of the magnetization. And it has and any perturbation that you apply to this system, it will relax back to equilibrium, the so-called M0, and it'll do it with T1 and T2 time constants. So the coupling between the M and the B is the so-called gyromagnetic ratio. The magnetic fields we deal with are the static fields, the radio frequency fields, and the gradient fields. There's a whole course that I have given on MRI. What we're interested in particular, in order to generate signals, is detecting the actual precessional motion of the induced magnetization. So initially we have magnetization, say, oriented along the z-axis. In the case of an MRI, if you're laying in the magnet, your head will be along the z-axis, your arms will stick out x and y. And the magnetization typically will be induced along this z-axis. If you apply a resonant and polarizationally matched signal, you can tip this magnetization anywhere on the surface of a sphere, centered right smack in the middle of the magnet and right smack in the middle of your head or your body. And then this magnetization can be tipped, let's say 90 degrees over to, say, along the y-axis. And you can do it fast. And you're actually applying a pulse to the system to do this, a radio frequency pulse. And then you tip it over, and then you stop, and you just watch and wait and listen. And what occurs is the magnetization decays with these T1 and T2 time constants and returns to equilibrium. And so this is the classic Bloch equation which is the basis of NMR and MRI. So what we do in fractional calculus, of course, is we've never seen a differential equation that we can't change the order, right? I mean, it's just, first thing we do when we see a d by dt or a partial with respect to x is, let's see if that could be a fractional order derivative of some flavor or some type. So clearly we could change the order of the magnetization here. And just to pick something, I've changed the time order from t, partial with respect to t, to a computo fractional order derivative in alpha and beta. And just to keep it most general here, for the T2 relaxation, I've allowed it to involve a parameter alpha, and there's no reason alpha and beta have to be the same. T1 and T2 are substantially different processes. So we can have a time rate of change of the beta, both time derivatives, and one involving the XY component of magnetization, the other the Z component. I mentioned earlier that the great thing about fractional calculus is it takes all these wrenches that you have packed in your mathematical toolbox, and it replaces them with one adjustable wrench that you can just work with. And I think I've lost people again.
It's okay. We can still hear you.
Can you see the slides?
Yes, we can see it.
You can see the slide. Okay,
No,
we're here.
No
okay,
discontinuity.
Okay, yeah. So anyway, so I indicated that there was this adjustable wrench that you have to apply to your problems. And that one wrench would solve all your problems. Well, that's not the way life works. You need more than one wrench, as Professor
That's a good.
knows that there's not a single fractional derivative that solves everybody's problem. There's a whole box full of fractional wrenches with Avogadro's number of definitions, I think.
Nice.
And in addition to the toolbox full of adjustable wrenches, there's a shameless variety of definitions for alphas and betas and gamas and deltas that everyone, there is no consistency. Professor Maynardi loves to call things alpha that I call beta and vice versa. So just because you see an alpha and a beta doesn't mean it's a time derivative or a space derivative or you have to be very careful to make sure that that what you're seeing in a paper or in a textbook is what you are thinking about, and make sure that that definition and all its subtleties are appropriate for the problem you're working on. It's an inconvenient truth that the alphas and betas are often flipped in publications. Speaking of publications, the work I'm talking about today is just, I think it's online now. It's just been published in the critical reviews of biomedical engineering. It's as a review paper. So I just went over the galley proofs yesterday. Or I'd gone over them, they fixed them, I'd gone over them, they fixed them anyway. So if you want to get more details, you can find it in that journal. So what we find with fractional calculus, as we always find, I'm preaching to the choir here. I'm telling you what you already know. We know that if we alter the dynamic response of physical systems of almost any form, that with a fractional model, the exponentials are converted to Mittag-Lefflers, and the decays then start off fast and then fall away much more slowly. And so here, just to be concrete, I've left the Z component alone. So I've set the beta equal to 1. I've let the alpha component for T2 vary. And so what you find here is you have these little corkscrews that I showed you earlier. But now these corkscrews, they decay at a rate that depends on the relaxation time. Here's a 50 millisecond relaxation time, short. Here's a 100 millisecond relaxation time. It is slightly longer. But you see that as the fractional order changes from 1, which is the exponential case, to 0.9 to 0.8 to 0.7, the decay goes faster. So the actual dynamics of the system are affected by when you apply your fractional model. The way I look at it is that the system is never a single exponential. It's at least a multi-exponential. And if it's multi-exponential, there are shorter and longer components. The fractional calculus is a convenient way of capturing all of those components. Okay, so that's about all I wanted to say about relaxation. I wanted to use it as an example of how.
We're gonna freeze. So Zoom, don't get restarted, please. So nice. T1, T2 relaxation.
See, it does work. It just
restart.
I did test this. Okay, now I have to go back to share screen.
Yes.
This is just making sure you're awake.
That's actually a good way to reset.
Okay, so screen's back, everybody. You see the screen now?
Yeah, we can see the yellow.
Okay. Okay, so the screen's there, I'm here. Okay, and I wanted to talk about diffusion. So diffusion is important in the brain for a whole bunch of reasons. the brain is a very complicated organ. I don't have to tell you that. Even the images are very complicated, and they're complicated at every scale, whether you're talking about microns, millimeters, centimeters, or the whole brain. The convolutions of the cerebrum, the white matter interconnections between the computational nuclei within the brain are all connected in ways that cannot be easily probed, except with MRI. And as we know, MRI non-invasively, well, you're getting radio signals sent through your head and you're putting your head in magnetic fields, but those signals, as they vary in time and space, are detected and then used to generate these images. And then on the image, in this case, the corpus callosum, you can generate patterns of contrast that tell you something about whether it's red or yellow here, about whether these fibers are larger or smaller diameters, whether they're closely packed or loosely packed, whether the myelin sheaths around them are impermeable or permeable. And so changes in structure are captured in contrast on the image. It's all embedded in the Bloch equation as appended by Torrey. And what he did was he just added diffusion and added flow. What we have now is an advection diffusion equation, where the forcing term is actually the MRI signal. We have a relaxation term, we have a diffusion term, we have flow. And so depending upon the magnetic field gradient, you can select out the flow, select out the diffusion, or tease out different aspects of the T1, T2 relaxation, as we talked about. So to do this, you have to turn on and off magnetic fields as a function of acquisition time. And this whole thing is repeated line by line by line by line to build up the whole image. And then these signals are applied in such a way that the time between the pulses allows the water, if it is diffusing or flowing, to shift its intensity. So what you end up getting is and this is the classical theory, you get a time rate of change of the transverse component that has a relaxation component, has a diffusion component, and then has basically a gradient term that you can adjust. So this is your input, the magnetization is your output, the physical parameters you want to get a measure of the T2 and the diffusion. And in the simplest case of Gaussian diffusion, believe it or not, this thing just falls out as a simple exponential in terms of a funny group of parameters and the diffusion coefficient. So the diffusion coefficient is millimeters squared per second. This B parameter is the inverse, seconds per millimeter squared. And all the little Greek alphabet symbols here refer to the amplitude of this pulse, the width of this pulse, the separation of those pulses, and the strength of the gradient. So you get to control every one of these parameters. You set the B value, and then the signal intensity should decay as a function of diffusion. So whether you're looking along the corpus callosum or along the fibers or across the fibers, whether you're looking in what is a superior or inferior direction across the tissue, you will get different values. And so you can build up the whole tensor image of the diffusion process. And life would be good. This is exponential. So if it's exponential, what do? We plot it on a semi-log scale. And if we plot it on a semi-log scale, we would expect it to decay as a straight line. And it does. But it does it in a very uninteresting place. Well, not totally uninteresting, but in the cerebral spinal fluid that bathes the brain, it's just saline with some proteins in it. There, on a semi-log scale, this exponential is a straight line as a function of this B parameter, which is something you can adjust. When you look at the gray matter, it looks sort of straight, but as the B values get bigger and bigger, or as the diffusion time gets longer and longer, the process curves a little bit. But when you look at the white matter, there's a lot of curvature. This is not an exponential decay. This is at least a multi-exponential decay. This is where fractional calculus folks like us get excited. When we see a process that is not exponential, it's non-exponential, it's non-Gaussian, then we start thinking that fractional order models might be able to capture this kind of behavior. And that's what I saw, and that's what I tried to do. So I went back to the Bloch equation. I pulled all the stops out, and did the usual process of going after the of changing the time derivative to a Caputo derivative, changing the space derivative to a symmetric sequential Riesz derivative, and wrote something down that was really pretty, but I couldn't solve. Matter of fact, in the general case right now, it has still not been solved. There's some people working on it. But for some simpler cases, I could solve it. And what I found, surprisingly, was in the simpler cases of let's keep a regular time derivative and let's just go to a space derivative that's symmetric. What I found was that you could get a very nice map of brain tissue for the diffusion coefficients that gave you some of these parameters, these mu and beta parameters that show up, where beta is the order of the space derivative and mu is just in there to keep the units honest. And what you get is you don't get an exponential anymore. You get the intermediate function between a Mittag-Leffler function and an exponential, the stretched exponential. And it turns out a lot of people had been applying stretched exponentials to this kind of data just as an ad hoc function because they knew it had a fast component and a slow component. But it was a heuristic approach. Here, I at least showed that under some conditions, restrictions on the fractional model, typically a time derivative of t, so that we got the diffusion straight, we get something that involves and invokes a stretched exponential. So this fell out of the fractional version of the Bloch-Torrey equation. But there's more. If you look more generally at diffusion as a fractional process, where you have a time derivative and a space derivative connected together. And if you think of the NMR problem with really short pulses, then the really only important parameter that you need is the separation time between the pulses. And then when you do that, you can then actually show that the solution to the Bloch-Torrey equation looks pretty much like this equation here. This is a Mittag-Leffler function, it's one parameter, order alpha, as a function of time alpha, goes right with that alpha. The beta then is a function of the Fourier transform of the space component. And so this is the Fourier transform raised to the beta power. If you take the Fourier transform of this equation, you'll get an ordinary Mittag-Leffler type fractional time equation where this parameter here goes to minus k to the beta times d alpha beta. So what you have here is the characteristic equation, the Fourier transform of this PDF, which is a general fractional diffusion equation. If you look at this in sort of a phase diagram, you'll see this again, where I'm plotting alpha and beta. Be careful about alpha and beta. Alpha and beta are not the T1 and T2 relaxation times anymore. I've pulled the wool over your eyes. Alpha is now the time derivative for the diffusion equation, and beta is the space derivative. And it's a symmetric Riesz derivative because there are at least 10 different versions of this beast. What we know in this alpha beta phase diagram is if beta is 2, we have a Laplacian. If alpha is 1, we have an ordinary time derivative, and we get a Gaussian right there. And that Gaussian at alpha 1, beta 2 corresponds to normal diffusion. And for reasons I don't entirely understand, in normal diffusion, every time beta gets a smidgen bigger or smaller than 1 or 2, it's always normal diffusion because the processes collapse back to normal diffusion. But there's a line going from the origin of this phase diagram to the Gaussian point of what they call pseudo or quasi-diffusion, quasi-normal diffusion. And what that means is that the mean squared displacement of the diffusion process along this line goes up as t to the power 1. It's a linear increase in time, even though there's a mixture going on of sub and super diffusion. So this phase diagram classifies different things that are happening in the tissue. If you think of the tissue as all subdiffusion, that is the water's being trapped. This is what the CTRW model tells you. But if you imagine tissue surrounded by capillaries with lymph channels, with periodic pulsatile motion driven by the heart, you might expect some transient flows in this tissue, which would move the fluid at a slow rate, but much faster than diffusion. And so in that domain, you might expect something involving like superdiffusion. So these processes are ongoing in a complex material. They are amenable to detection through MRI, through the diffusion process, in a fractional diffusion equation, as long as we have a short pulses. And the surprising thing is that this is math, this is fractional diffusion, this is the Fourier transform solution of that equation. It's the characteristic equation, if you will. This K here is directly detectable in MR experiments. It's called Q, but miraculously, this is what you detect. And so this relationship is, we're not taking data, manipulating it in some complex way, and then trying to fit it to some obscure function. The dynamics of the MR process and the solution to the fractional diffusion give you this relationship, where the beta for the fractional space derivative multiplies the spatial frequencies, and the Mittag-Leffler time decay of the space of the time derivative goes with alpha. Anyway, so what we did is, of course, took some brain samples. These actually came from some rats. And we fit this data as a function of B, and saw the same sort of thing as before with cerebrospinal fluid, with white matter, and with gray matter. And then we looked in different regions of the brain. So what we see here is we're on a semi-log scale. So everything in the brain is not linear, so there's no straight lines. But you see these little circles here, 1, 2, 3, 4, 5, 6, 7. These are different regions of the brain. And so these regions down here, these big circles, the ovals, the real circles, 1 and 2, they correspond to gray matter. 6 and 7 correspond to the regions right here where you have squares. And this corresponds to regions that are mixed white and gray matter. And the dark areas right here, the 3, 4, 5 correspond to the corpus callosum. And in that region, it's all white matter. And it's very, very multi-exponential. And so what we do is we fit the different regions of the brain where the structure is known by the neuroanatomists to our NMR data. And now the Q and this delta are the analogs of the K and the T that comes from the fractional math. We need some constants in here to keep everybody honest. But these experiments were done by one of my PhD students, Carsten Ingo, and they were published in MRM. And again, as I told you, what you get is you get these pictures and graphs, but you can go further because you can apply this graph and this process of extracting alphas, betas, and mu's and tau to every single pixel in this image. And so you get lots of images. You get basically an image here for each parameter that you're fitting, and you do it for each pixel of that image. Here's some prettier versions of it. So here's alpha, here's beta, the fractional time and space derivative. Here's the diffusion coefficient. Here's the mu and tau. And here's sort of an entropy, normalized spectral entropy that.
I'm going to restart. I think maybe this is a feature of Zoom, so I keep everybody awake. So you periodically reset and restart. So let's just wait a little bit. So this figure is significant, I tell you. It's significant, alpha, beta for each pixel, okay? Richard, don't worry, take your time. So, but remember, you have how many pixels? So each pixel is a fractional order differential equation. You need to fit the alpha and the beta.
Back on. Okay, I'm
okay,
back.
that's great. I'm trying to fill up some of your time.
Yeah, okay.
So you have thousands of fractional order differential equation you need to fit the Mittag-Leffler fitting, right? So the speed was painful initially, right?
Right, and that's one reason why we keep trying to simplify these things.
Yeah.
Let me, let's see, I need to turn on the
alpha map, beta map, you are there, that's that slide.
Yeah, let me share the screen again. Okay, you got the screen now?
Yes.
You guys see this?
Yes. It's a slide before this one. A slide before this one. Before that. Yeah, this one. We were at here.
Right. So in this initial experiment, we drew regions of interest on parts of the brain that we were told had a characteristic type of structure. And then we were just trying to see, here's the error bars on the measurement. Here's, and the separation between the curves give us confidence that what we're seeing is complexity in the tissue. So, and so then we apply this technique to every pixel in these images. Okay, it did take time. If you read the fine print here, the MLF, the Mittag-Leffler function, and entropy parameter maps for a slice of a fixed rat brain. So this is a rat brain about the size of a walnut or pecan, and it was it was dead, it was fixed, it was put into a test tube, it was put into a 17.6 Tesla magnet in Gainesville, Florida, and it was left there overnight. So after about 12 to 24 hours of imaging, we got this data. So it shows that it can be done. It doesn't show you that you can do anything in vivo clinically yet. But if it's not worth doing, it's not worth doing well. Another one of my sayings. So we have to show that it's worth doing. And what we, to move on to try to do it well, you have to cut some corners. You have to simplify. So Tom Barrick and Matt Hall, who some of you may know, have applied fractional models to clinical cases in London. And in these studies, they've used our friendly Mittag-Leffler function here, E sub alpha, D alpha beta, the diffusion, Q to the beta, delta to the alpha. But there's all these parameters, and it takes, as I said, hours to get the data. Okay, they did it in this set of experiments on patients in about 228 seconds. Okay, so they're doing it in what, about 4 minutes, right? And so this data then, in order to collect this, you have to make some assumptions. And the assumption they made was that we're not going to try to map the diffusion into this entire phase space. We're going to, for reasons of simplicity, assume that the processes are more or less, most of the water is going to be quasi-normal diffusion. And there'll be some variation about that. And so to make the water quasi-normal, we'll just set 2 alpha equal to beta. This is just pulled out of their head. And when you do this, what you find is that all these parameters collapse into this nice little equation. And this looks like a stretched exponential, but really it's a stretched Mittag-Leffler. And it's a stretched Mittag-Leffler where the B and the D are really nice because they're multiplying each other within the stretching term. So they have regular coefficients. They have regular units. There's nothing peculiar about them. So this can be done quickly. These are, I think this is Tom's brain, and it can be done with relatively few measurements, and it can be done with encoding that gives us some of our fractional information. I think he's got another, there's another slide I got from Tom where he actually applied it to patients. And so this is some stuff he published last year in NeuroImage. And these are patients with tumors, and the tumors show up with different contrast in normal imaging. This is T1 relaxation imaging. This is normal diffusion imaging, and here are the fractional. And here are the fractional measurements where the alpha beta parameters are measured, and the entropy parameters are measured. And what they're looking for here with these arrows are regions where there's not much contrast in the normal images, but there's hints of contrast or different shades of gray in the fractional model. We're looking for features that could be perhaps related to unknown changes in structure that you can't see with the conventional technique. So this gave us some confidence that it's possible to do the imaging in an efficient way and still get new and perhaps useful medical information. And now these guys, this group and others have gone on to apply this to other larger groups of patients. Muge Carmen has done this on some patient populations in Beijing, I think. And in this study, they've looked at some human brain tumors, and this is data taken from children. And she has kept the model in a, and this is the heuristic. This is not, not the full simplification of beta equal 2 alpha, but it's a simplification that keeps a beta, but keeps the diffusion coefficient coupled. So in this particular model, again, the data can be obtained fairly quickly, but you get different patterns of contrast in the beta, in the alpha, in the D, that in some ways give you more information and that could be more useful. One of the big questions with these brain tumors isn't, do you have a tumor? Typically, that's what brought you to the hospital. But the question is, when you're being treated for that tumor, is the treatment doing any good? If you start the tumor on a child, the tumor grows fast, the child's growing fast. If things aren't, if the treatment doesn't keep up with the tumor, the child is going to die. And so you have to change it quickly, and you can't wait a month or two to see if the tumor has doubled in size. I mean, when tumors are this big in your brain, doubling in size is not an option. A 5% change in volume can be lethal. So you need to have some way of getting information. You can't stick needles in and take samples. And so these models, we think, have this potential. And in particular, they differentiate between high and low grade tumors, and they can show some of the early changes that occur with radiation or drugs, when it's effective, when it's not effective. Anyway, there are several other, in the review I mentioned, there are several other things that I could show that are works in progress that are trying to extend this. But just to sort of wrap things up here, I want to try to put into context these different models. So here's the phase diagram that I talked about earlier. That's this orange slab here. This is the beta and alpha. And beta and alpha are the time and space derivatives that I've been talking about. But look what I did. I told you to pay attention. Those of you that are sleeping out there, I flipped the betas and the alphas. Beta is now the time derivative. Alpha is now the space derivative. I'm sorry, you have to stay awake. And what you see in the mean square displacement here is a power of time that isn't a simple linear one. It's 2r over 2 times r, where r is this ratio of beta over alpha. And so the mean square displacement is clearly non-linear. It's non-Gaussian. And it depending on where you are in the phase diagram, you have a different equation, right? I mean, if you're going to do Gaussian, here's alpha, beta in these new definitions, and here's the diffusion model for the Gaussian, time derivative and space derivatives. And then if you have the full CTRW model, you have beta on the time derivative, alpha on the space derivative. You have the alpha and beta, and this is what's being fit with this function here. This is what is in the background. You have other cases of where you have maybe just a fractional time derivative or just a fractional space derivative. So there's 4 possibilities here. You can have things like CSF that are normal diffusion in a fluid type or homogeneous environment. You can have the full super subdiffusion models of sub and super of the CTRW for for very complicated tissues. In other cases, you might be able to argue that the fractional space or fractional time derivative are the only things you need to worry about. So you can look at this phase diagram here then as connecting the alphas and the betas. But people are using these models in a more general manner. That is, they're relaxing the stochastic, remember I told you there was some stochastic component to this, the stochastic constraints. In a CTRW model, you have independent processes in time and space that are either trapping or affecting the distributions of jumps. But the motion is completely random, and there's no persistence or anti-persistence. There's no likelihood that if you're heading down the hallway, as you will be as you run away from this lecture or a seminar at the end of class, that as you go down the hall, you might bounce out of the wall, but you're still going down the hall. There's not a big likelihood you're going to stop and go the other way, at least not until you get out of the building. And in fact, there are other models that show this kind of behavior. So here's another fractional model that Muge has applied that involves a so-called fractional motion model. And so here the math gets a bit tricky, because what we're doing here is we keep the time derivative as 1, so we get an exponential, not a Mittag-Leffler, but we've got these phis and psis popping up here. And what these are doing is they're connected to the likelihood of the diffusion being persistent or anti-persistent. And so within the fractional motion model, you imagine that the complexity of the tissue affects the movement in a way that you get an altered statistical process. And it turns out this thing can be modeled quite nicely by a Riemann-Louisville fractional integral. And that this process then involves something called the Hurst exponent. And this is an H here where we had an R before, and the R before was the ratio of beta over alpha in our conventional model. Here the H exponent now involves a fractional derivative and something else. Okay, so I made a little diagram here. And so what we have is the Gaussian case here, and we have the fractional motion case. Look carefully at this fractional diffusion equation. The fractional part of it is the fractional space derivative called alpha here. The time derivative is integer order, and we get a diffusion coefficient. But oops, what happened to the diffusion coefficient? It's no longer a constant. We're allowing the diffusion coefficient to be a function of time, in a particular, a function of time that varies as a power law, either increasing or decreasing. I mean, if you're going to model mathematically, you have to use all the cards that can be dealt out. If someone's going to deal hearts or diamonds or spades or clubs, you have to try to put them together in your hand. If you can take a constant and turn it into a tensor, so be it. If you can take a constant and turn it into a function of space or time or even concentration, those are possible things to consider. And in this fractional motion model, what we're doing is we're allowing the variation of the diffusion coefficient to be a power law called gamma in this case, that
we're going to freeze. This is very interesting. So there's a difference between fractional order diffusion versus fractional motion diffusion mode. So basically the coefficients are time varying, the DH alpha.
Okay, I'm back.
Okay, great. That's excellent.
One more slide, then I'm going to be done.
Sure.
But anyway, I just, okay. So so the point here is that the fractional motion model it has a time dependence in the mean square displacement, and that time dependence there involves this Hurst parameter and this gamma and the alpha. Well, I saw this and I figured, well, that's crazy. I can't handle two kinds of fractional derivatives. How can I handle two kinds of stochastic Brownian motion? Well, when I was looking at this, I realized, well, I'm only handling one kind because beta is equal to 1 and alpha is the alpha I know. I said, well, what do I know? Well, what we know is back here when we were looking at the problem in our Gaussian case, we were in this alpha beta plane and there was no gamma. So gamma must be 0. So here, gamma equals 0, that's alpha beta plane, that's the bottom or the ground floor of a cube. The back wall of this room is the situation where you can vary in alpha and you can vary in gamma plus or minus 1. So the back wall of this cube is the phase diagram for fractional motion. And the situation of the quasi linear or quasi Gaussian diffusion occurs right along this line here. And this is all taking place on the back side of the cube. And so the more I looked at these models, what I found is that when you start to allow the space or time derivatives to be fractional and you allow the diffusion coefficients to be fractional in time or space, then what you get is just a whole collection of models. And they're not random. It isn't a quilt. It's not a crazy quilt where you go and collect little pieces of cloth and make squares and put it together into some crazy quilt. It is something that actually, to me, it makes sense. When you have a CTRW model, you get a z equals 0 plane, it's alpha beta. It has a mean square displacement that goes as 2 beta over alpha, and it is corresponding to a fractional diffusion equation with a constant coefficient. When you have a fractional motion model, you have the situation where you have the back plane of this cube, and the back plane of this cube corresponds to beta equal 1. Alpha goes in this direction, gamma goes up and down. So you have a mean square displacement. Again, it's not linear. It has a different relationship here as it goes, but it corresponds to a diffusion equation where you now have a diffusion coefficient that's an inverse power law function of time. So there's a gamma in here and an alpha. There's another case that's in the paper that you can look at that corresponds to where, what if you take the same equation and now keep the time varying diffusion coefficient, but instead of doing a space fractional derivative, do a time fractional derivative. It just flips to the other side of the room. So instead of having the back wall, now you've got the left wall. And so the gamma is now the third axis, this so-called z-axis that I'm talking about here. And so when you have power laws in time that are gammas going up and down in the back wall or the side wall, you can then flip the betas or the alphas as you need to fit the process that you're trying to work with. And of course, the next logical step is to do both. And the next logical step is to do it again with diffusion as a function of position. And then look at maybe diffusion coefficients that are a function of time and position. That's the next paper. So I've run out. Okay, so the neat thing here is that the equations make sense. You're now fractionalizing not only the order of the operators, but you're doing what you normally do with advection diffusion. You're allowing the diffusion coefficients to be inverse power law functions of time. And when you do that, you alter the mean square displacement from the linear to the beta over alpha for the CTRW, the sort of 2H parameter variation, which is what you get for the fractional motion. And then you get here, it's even in some ways even more interesting because now you get the fractional parameters being added. So here you've got the ratio, they're divided. Here you get the ratio of some products, and here you get the sum. And so these are different phenomena. There are different parts of the brain that may or may not be more suitable to being modeled by these things. So anyway, in conclusion, connecting the dots here before my computer goes away. Diffusion is anomalous. Anomalous diffusion is everywhere. And fractional calculus models are versatile.
Cool.
All this work was done by everybody else. Everyone always says this, like we don't ever do. But in this case, all of these collaborators have been involved for at least the last 5 years in this project.
Great.
So let me think. So I got some time here. I'll be happy to answer questions. Two little things. If you're interested in diffusion and relaxation, there's an active study group that's run out of Brisbane. If they didn't get rained out in their rainstorm yesterday, and if they're not suffering because the Indian cricket team beat the Australian cricket team. But other than that, they're usually studying relaxation and diffusion. And so this study group, there's a whole bunch of webinars, mine included, that you can go to, and you can look this up. The work I've talked about here is coming out as we speak. It'll be out in the next week or two. And the general scheme we're talking about here is to try to model problems in medicine using fractional mathematics. That's what I'm trying to do. Okay, so I'm done with slides and things. So if you'd like to chat, I'm here to chat. I have nowhere to go since I just took my wife to the airport and it's dark outside. Okay.
That's great. So maybe we have a meeting at 4, but I can join late. So Jairo and Jairo and Kai, you guys can start that meeting. But I'm going to stay about 10 minutes and join you later.
Do you want me to unshare this, or did you unshare?
Just leave it there. I guess we can extend the discussion for 10 to 15 minutes. So these young people will benefit the most from your wisdom.
Flaky internet. I'll blame Ponce de Leon for
the first thing in my wish list is you mentioned about the version 2.0 of first, best, and different. you haven't shown that yet. This is the first in my wish list. Second on my wish list, I smelled that you already solved my puzzle about the question I have been thinking for a long time. That is called space-time duality. In other words, you have a fractional phenomenon you describe in time fractional, but there could be an one-to-one related characterization using space fractional to do the same. So I know that Mark Marshall has a paper on that, but from engineering point of view, I wish what I said is true. So space fractional, time fractional, especially now today you introduced the phase diagram, Magin diagram.
No, that's not my.
Will help us. Will help us to have a deeper understanding.
Right. I mean, the Gibbs phase diagram.
Yes, you mentioned about it.
The phase rule to that diagram. That's something I could do.
Yeah, you mentioned the Gibbs. Yes.
Yeah.
It's amazing.
But that's all his stuff. Yeah, you're talking about the good, better, different, or good, best,
first,
different.
Best, different.
First, best, different. Yeah, what I'm telling my students now is something I got from Arthur Ashe, a tennis player, and what he used this in guiding his training. When you thought about what you were going to do every day, you start where you are. You don't try to train as you were trained a week or a month, or you hope to be trained a year from now. You start where you are, you use what you have, and you do what you can. And you don't leave the room, the table, the computer until you've done all three. Otherwise, if you don't start where you are, you're speculating about what you might do if you have more. Well, in which case you're not starting where you're at. And if you don't use what you have, you're not doing anything because you're thinking, well, if I had more, I could do more. And then you don't do anything. And then you do what you can. And so it's a way to get things done.
Okay. All right. So thank you, Hong.
Sorry I can't be there, and sorry we can't.
This is excellent insights. Yeah. We'll exchange opinions.
If they want to send me an email,
yes,
you got my email address. I'd be happy to chat about this. And then what I'm hoping is maybe someday we get this virus done with. Come visit. Since I've officially retired, so I don't have to teach. So I'm an emeritus professor, and I'm free to travel. Right? I should be able to come and visit and stay. Like I go to Slovakia to visit Igor. I stay for a month. I mean,
yeah, that's cool.
You get tired of me in about a week, but I could stay for a month, and that gives you time to really talk about where there's an overlap and trying to see what you could do and how you might do it together, or do it differently, or do it better, or do it for the first time.
I see. So I'm open the time for people ask questions. Hong, if you want to ask a question, you ask them before you leave, if you don't have another meeting. So feel free, you can go. You guys have some other commitments. We are going to spend another 10 plus minutes together.
Thank you, yeah.
Okay. The one thing I have real trouble with,
numerics, lots of numeric challenges.
It's so hard to get my hands on people because I want to be able to respond, and it's hard to respond to talking pictures. It's just, or better than that,
open the video.
It's so great with Zoom that we can do this. I mean, if we couldn't do this, I don't know what we'd be doing. But it still lacks a vitality or vitalism that you have when you're in a room talking to someone with a piece of paper between you.
Hong, do you have anything you want to comment and add insights?
No, thank you. I really enjoy the talk, actually.
Oh, good.
Long time no see. Yeah.
Yeah, well, I knew this was part of this class, so I wanted to have some background stuff that they could remember and think about. But I also wanted to show them that where these models meet the technology as it's applied, is in capturing the change in structure, and it's the changes in structure that are critical. I mean, because sooner or later, all of us will have a problem that needs to be addressed. And if you can't see it in the image, you can't deal with it.
Yeah. Great. Any other questions from our audience? Yan Li, you get up very early. Maybe you get a chance to ask a question.
Yeah, I would like to. Sure, I would like to ask.
8 o'clock in China.
Yes, I'm in China. It's early morning, but that's fine. My daughter needs to go to school, so I get up early every day.
Okay.
Well, that's the other thing about this group I was talking about has people in Australia and in London and in the US. So for some people, it's 9 o'clock at night. For others, it's 7 in the morning. And for others, it's noon. And so some people are eating lunch. Some people are just getting out of bed. I mean, they were doing it at 5 a.m. Chicago time. I mean, that's even early for me.
Oh. Hello, Richard. Long time no see. So, can you go back to slide 39? 39. Just one slide about the MRR image with fractional orders on it. 39, page 39.
39.
Right now we are seeing 40. You go back one.
Yes.
Okay, go back one.
Yeah.
Go back one.
Can you see it?
So.
Yes.
Yes.
Do you see that? Okay, now.
Yes, very clear. So I noticed the fractional orders on, seems like it is a fractional order on each pixel of this image. So how can we do that? I mean, for example, given an image, how can we compute those alpha, beta, and some other fractional orders as quickly as possible. So,
well, in this case, it was not possible to do it quickly. This took 12 hours.
oh, I see.
Right. That's why we were trying to do some simpler things, but we wanted to see if we could measure, given all the time in the world, given there was no motion, given that we knew what we were looking at, then we wanted to see, would there be contrast? And the answer was yes. Now that we know that there's contrast, you know, then there's something to shoot for in trying to develop a clinical tool, and that's what other people are working on. Is how do you balance the resolution and the precision with the acquisition time and the context that the physicians want to see the data presented that allows them to make their decisions. So, but the nice thing about MRI is that you slice the tissue up into maybe fairly thick pieces of meat, maybe 3 or 4 millimeters thick. But then within that slice, you can have maybe 256 by 256 or 512 by 512 pixels, each of which is a submillimeter. And so you can have pretty good in-plane resolution, but you're looking at basically noodles of the brain. You know, you're looking at a fairly thick vertical slice. So looking for something, when you start looking along a fiber, that's great. When you start looking across different sub-levels of the, of the cortex, where the connectivity is at the micron level, then there's a lot of coarse graining that has to go on. And so maybe the fractional parameters capture that, maybe not. But
I think definitely yes. I think.
Yeah, but in fact, every pixel has a curve like this.
Yes.
Right. And so and so I can and then from that curve I fit the parameters, and then I make the 6 images. My students, I don't do anything.
So you need 10 hours, 12 hours to do this.
To collect the data, yes.
Yes. I mean the fitting.
Oh, the fitting, I think he did it on his home computer. It probably took 12 hours too. Yeah.
So that raised the question.
That never bothers me, because if it's worth doing, it's worth doing well.
For numeric analysis, Professor Hong Wang, we need your fast algorithm. I was so impressed by your fast algorithm.
Yeah, he's good.
Want to do it faster, yeah, and faster. There's a lot of talk about how to do it faster now. But if it's not worth doing, it's not worth doing well.
Yeah. I actually have a related questions.
Sure.
Does this mean your order alpha beta depends on the pixel and time? The position of the pixel somehow?
Yes, and we hope that it's because the pixel, although it's, think of it as, say, a cubic millimeter.
Right.
Okay, well, a cubic millimeter is made up of cells. Cells are a cubic micron. There's 1 million cells in a cubic millimeter. And there's untold number of combinations of those organizations of those 1 million cells. So this is really coarse graining. And so what we're hoping is that there's subvoxel structure that's captured in the alphas and the betas.
Okay.
Cool. So I would like to say this alpha beta map, Richard is the father of. You invented this one for the first time. So you already had clinical evidence that these alpha beta maps, instead of the original map, actually can enhance the resolution and sharpness and so on and so forth, localization of those tumors in a much improved way. Is that right?
Well, the people I work with have done that.
Okay.
Yeah.
Oh, can I ask another one?
Sure. Go ahead.
Oh, yes. So I'm also wondering, what are the relations between those fractional orders and some indices of the human body or the health of the human body. For example, the blood pressure, cholesterol level, or something. There's some such kind of relationships.
You would expect the alphas to change from position to position, but as you say, you'd also expect the alphas to change with direction. And you'd expect
the direction means the health, for example.
You expect them to change in time.
Exactly.
Yeah,
like the aging, something.
Exactly. The same kinds of, it's funny that if you look at embryos and you look at how they develop histologically, they get greater and greater complexity. And early on, the embryo doesn't have a lot of contrast in an MR image.
Yes.
But as the organism becomes more complicated, then that complexity starts to show up. And so you would expect the alphas to vary with time. And then, as I know, because I keep sticking my brain in these magnets, as I get old, the brain shrinks, it gets stiffer, and you know, and the number of active neurons goes down, and so it's the other side of the rising and decaying curve. So the alpha and beta parameters are certainly a function of age. They're a function of time. Whether they're subtly also a function of heart rate, blood pressure, those are good questions. And so you'd have to have a fast algorithm and a fast imaging scheme. And there are systems that can make an MRI image in a millisecond.
Okay.
Yes. That's,
I mean, because they want to stop the
yes.
heart, right? I mean, they want to image the beating heart, and the heart, and you have to have sub-millisecond resolution to do that. And with those images, you could then make these measurements as a function of diffusion time, and then you perhaps could get information. And probably what you want to do is look for a correlation coefficient of some sort, right?
Yes.
Measure something. Look for the correlation with, and maybe look for the phase or the overlap with the
heart rate.
The correlation in the beginning, and then some linear or nonlinear relations.
Right. That's the other thing I didn't talk about is there are nonlinear models and nonlinear fractional models.
Nonlinear. Okay.
That you can use here, where you can allow the p to be raised to some fractional power.
I see.
So you have a nonlinear equation, and that's typically the way you handle these systems. And
I have a question about early detection of Alzheimer's disease. Suppose we can do this alpha beta map every week.
Yep.
And we can do this one for 10 years. I have a 10 years track record for a specific person. So physiologically speaking, or physically speaking, we can do the early detection of the Alzheimer's disease or not?
I've done some studies on mice that are genetically modified to exhibit changes in their brain that mimic Huntington's disease, Alzheimer's disease, and sure enough, as the mice age, they naturally get, just like we do, some of us, unfortunately, they exhibit these symptoms early on, and then you can measure the physical symptoms, and then of course as they get older, then there are overt. You can see they have trouble walking, they have trouble going through a maze, and so the question we asked is, can we see any changes in the alpha beta map before they exhibit any cognitive or motor disruption? And we were able to do that in a couple of cases. This is work that's just been recently published by Rodolfo Gatto and some other people at UIC.
Yeah, okay.
So we've seen that, and that's exactly what we're trying to do is find a model of the disease in an animal. And then what you want to do is you want to do the imaging, and then you want to sacrifice the animal, and then take the brain. You want to look at a live animal, you want to take a fixed brain, then you want to take that same brain and send it to the electron and optical microscope and section it and then try to correlate. These take time. then you look at those regions of the brain on the electron and the optical photomicrograph aligned with the slice where you collected the MR data.
Nice. Yeah. Well, any other final urgent question? If not, we can
you guys to go
stop
home.
here. Thank you, Richard, for inspiring the young minds.
Good to see you all. Thanks for listening. If you have any specific questions or if it's not clear where to follow up on some of this information, send me an email and I'll send you the reprints or the links.
Excellent.
Thank you.
Excellent.
Thank you.
Thank you very much.
Okay.
So,
thank you very much.
Bye-bye. Take care, everyone.
Bye.
Thanks.
Bye.
Bye. Take care.
Bye. Bye.
Remember Ponce de Leon.
Okay. Thank you for introduction. Yeah. Yes. Bye-bye.
Okay, bye-bye.
Have fun.
Bye.
Bye-bye.